Hello everybody and welcome to another fabulous and fantastic and analog juiciness from the Escalate Data. Today we're going to be doing some more hacking on that MEMS microphones. That's the analog juiciness, and then I might also lay it out if I have time. This is a project I'm working on, sort of a long-term project, which is Circuit Playground, which is designed to be sort of a all-in-one Arduino compatible type experimentation board, because we get asked a lot by schools and universities and even companies that are like, well, we want to have a hack shop, but we want to have something that doesn't have any soldering or even breadboarding. Like, that's right, even like breadboarding is a little too complicated for some students, so they're like, well, we just want something all-in-one. And so I'm adding all these sensors to the board, and I have a spot, like right here, you can see this empty red spot. That's where the microphone sensor is going to go. And I actually started working on this like a week ago, but I had like a really crummy head cold, and I kind of spaced out in the middle of it, and I couldn't remember my emitter-degenerated BJT calculations, and it was like midnight, so I stopped. But I'm ready to get back to it. I pulled it apart from the breadboards. I'm going to start over from scratch, and I'll just rush through the beginning part of it. But let's go to the overhead, and we'll have scope cam later as well for people who are looking forward to scope cam. No cat cam instead, it's scope cam. So here's the breadboard I'm going to be working on. And I've got this MEMS mic. It's out of focus, but you can kind of see here. There's in the center is the microphone, and then some analog circuitry around it. So I'm not going to use any of the analog circuitry, which is actually mostly just decoupling caps. There's a power supply, a 3.3 volt regulator on here. There's a 3.3 volt chip, MEMS chip. So I'm probably going to have just the sensor itself. I don't need a decoupling cap because I have a bunch on the circuit board already. And basically, you power it with 3 to 5 volts in ground, and you get analog out. So the reason I'm going with a MEMS microphone instead of an electret mic is basically to make this as low cost and easy to manufacture as possible. I want to have this pick and placeable. An electret mic requires hand soldering because it cannot go through a reflow oven. So it would be like we would reflow all of the parts except for the electret mic, and at the end we would put the electret mic on and solder it. Also, electret mics are kind of like, they bump up a little bit. They're a little tall, and so there's mechanically, they have to be soldered on by hand, which is annoying because it's a hand step. I like to avoid those if possible because pick and place is so fast. And then secondarily, they stick out a little bit, and then the mesh on top is gets scratched up pretty easily. And so I kind of like the idea of a MEMS mic. Now, it's not washable because it's a port, but it's still better than I think an electret mic. And electret mics, you definitely need an amplifier. And you need a pretty reasonable amplifier. Like, you have to give yourself a gain of 200, I think, at least. Whereas with these, because it's microvolts, under a millivolt, I think, is what you get out of an electret. Whereas on these MEMS mics, you get a little bit more. And so I don't need to get a full 3.3 volt out. I'm not doing high precision audio calculations. I basically am just going to be measuring volume, audio volume. So I just need maybe a half a volt or to a volt peak to peak. And then if possible, if I can get enough room there with amplification, I can do some fast Fourier transforms, like, not a lot of bins, but enough to maybe have some audio reactive projects that listen to bass and treble and mid-range. That's where I'm at. Okay, so let's grab our scope probes and let's check out what we're getting out of the microphone as is. So I'm just going to plug into the DC out, and then let's go to scope cam. Okay. And I'm going to...
Oh, no.
Scope cam froze.
Scope cam froze.
Okay. You want to try to fix it?
Yeah, I am.
Okay. Hold on, everybody. I'm just going to do a jig. So now you know I'm alive. Jig, jig. Jiggity, jig, jig, jig. Yeah. It's angry because it wants to be cat cam.
It's not scope cam.
That's a different cam. I don't even know which cam that is. It's one of the ones back there.
Scope cam is back. No.
No. It's plugged into this USB extender. Do you want to just Okay. Jig time. Jiggity jig 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 jig. Anyways, meanwhile, I'll talk about the project some more. So that's cool. Yeah, I just unplugged it because it went to a question mark. So far I've got a light sensor, temperature sensor, speaker. Oh, there's scope cam. Oh, yeah. Okay, so we're live and we're scoping. Okay, I'm just gonna shove this over a teeny bit. Okay, great. So we see here. Let's put on the measurement. There's about 680 millivolts of DC offset. That's from the data sheet. Last time I looked at the data sheets, that's about right. I want to put it into AC coupling mode so I can get this from. Other way. Oh yeah, my oscilloscope's great, but the encoder's kind of iffy. I kind of have to twist it a bunch. Okay, so 20 millivolts. So there's a lot of noise because whatever coming from the USB and then it's regulated, but I don't have a hardcore regulator going on here and filtering. And then if I speak into it, you can kind of see the it's picking it up, and I'm getting if I'm about a few inches away, it's 50 millivolts peak to peak, basically. So about 50 millivolts peak to peak is what I'm getting out of it, and I want to give myself at least 500 millivolts. 50 millivolts is actually just too small. Even though I can pick up it a little bit on a microcontroller, you only have especially on the microcontroller I'm using, you only have let me see. I think it's 2.5 is the AREF, and then I have 2 millivolts or so of resolution per bit for the ADC if it's 10-bit ADC, but honestly, there's already so much noise, and I want to have I want to be able to pick up sound even from this distance, so a couple feet away. So let's go to overhead cam. So overhead cam, you can do it, yay! And so we talked last time about how you want to amplify the 50 millivolts and maybe give yourself it'd be really sweet to have 200 millivolts at least. So, sorry, not 200 millivolts. I want to have at least 500 millivolts, but ideally I could get like 2,000 millivolts. That would be ideal. So, you're talking about a gain of like, it's not that much gain. It's like, you know, this is like times 10 gain, this is times 40 gain. So, you know, you can use an op amp. Op amps can give you like 1,000 or more gain, and, you know, you're going to have like perfect linearity with respect to how good your audio signal is anyways. But the deal is that like, I don't actually want to use an op amp. And the reason I don't want to use an op amp is, given I don't need that much gain and I don't need perfect fidelity, I just want to kind of just like boost the signal up. And for me, cost is pretty important. Like an op amp is like 10, 20 cents, especially if you want one that gives you rail-to-rail input and maybe even rail-to-rail output. They're not that cheap, and like the quiescent current is also like a couple milliamps. So it's not like having an op amp will save you power. It's just like you can get a lot of gain very easily, and you still need a bunch of passive components. So I wanted to basically go with a degenerated emitter, like sort of a semi-feedback transistor. So, you know, you have your transistor, and I'm not using it as a switch. I actually want to amplify the AC voltage. So what I'll do is, you know, you bias it with some DC, have your emitter resistance, and then have RL, which is your load, which is going to, it basically pulls down the voltage, and then you read your DC plus AC out of here, and then the AC is like times, you know, times your gain, and your DC is set by how much current is going through this transistor, through RL and RE. And what I forgot last time was the equation for gain, and like later on, I looked it up and I was like, oh yeah, that's right. It's really easy. It's just RL over RE. I don't know. I don't do electronics while sick. Okay, so then the question is, you know, how much do we want to bias this with? And you know, I'm a basic girl, so I'm just going to go with 1 milliamp. You know, you can always tweak that later, but 1 milliamp is a pretty good place to go. And the question is, you know, how low can I make DC? Because the larger you have RL and the smaller you have RE, the more gain you have. Remember that the negative gain means it's inverted because it's an inverting transistor. If this goes up, then this goes low because more current is going through here. So it's inverting, but I don't care because audio is it doesn't matter if you invert it because it's an AC signal that I don't care about the polarity of it. So you want to basically make RL large and RE small, but you don't want RE to be so small that you basically make this unstable, because even though I can get a 1% resistor here and I can get a 1% resistor here, I have to make sure that this voltage here, this VE, is pretty stable. The larger RE is, the more flexibility I have in the VE, because this, you know, voltage across this diode, the built-in diode of an NPN transistor, it's like 0.6, 0.7, you know, ish volts. I mean, it's just not like a precision value. You just can't guarantee it. We approximate VBE as 0.7 volts, but you know, you can't rely on VE. Like if you can't say VE is going to be 0.05 volts, like that's not within your accuracy prediction. So, you know, what I'm going to say is, okay, let's say that VE is about, I'm comfortable with saying it's about, you know, 100 millivolts. I'm okay with that. That's like, you know, because it is 0.7 to like a pretty good precision. And like the bias current will change a little bit, but that's okay. As long as I give myself enough of headroom. Again, I want to make RL large, but think about it. The more current that's going through RL, the lower this DC voltage is, because the DC voltage is going to be 3.3 volts minus IC times RL. So having RL be larger means the DC voltage drops, and you don't want to drop it too far because then you start bumping into this down here. So you want to give yourself a little bit of room here. You want to have this be at least 0.2 volts. That's kind of a good, little bit of headroom. A little bit more is good too. So given that, I know this is going to be 0.1 and this is going to be 0.2, I'm going to make RL be 3K. And I can change it later. RL can be the 2.7K. Like I'll maybe build a couple, see how the variability is of this BJT, and adjust as necessary. And this will give me a DC voltage of about 0.3 volts. Actually, I'm going to make this 2.7K. 2.7K. And then in order to make 100 millivolts turn into 1 milliamp, I'm going to make RE equals 100 volts, 100 ohms. So let me just redraw this nicely. So this is 100 ohms. This is 0.1 volts. This is 2.7K. Since this is a 3.3 volt system, this is going to sit at about 0.6 volts, which gives me plenty of room. In fact, I can actually make this 0.2 volts later if I want. And what's nice about this is it's just tweaking resistor values. So it's like once now that I have the architecture, I'm pretty much, good to go. I can tweak it as necessary based on actual usability. So I kind of like that, so that I don't have to worry about turns out I don't want an inverting amplifier. I want a non-inverting or whatever. Okay, so next up, we know this is 0.1 volts. This is going to be 0.8 volts, and then I want to set this bias here. So I want, 0.8, let me do the math, so 0.8 divided by 3.3, so I want something that's, let's say this is 10K, let's see, times, invert this. So I think this is 42K. I'll just do the math backwards. 10 divided by 52 times. Sorry, this is 33. I forgot to subtract. Yeah, okay. So this is 30K and this is 10K. And then I'm going to couple in my signal from the microphone over here through a 1 microfarad capacitor. Why 1 microfarad? Because that's kind of what I got on the rest of the board. I got a lot of 1 microfarad capacitors, and I don't want to have multiple. I'd rather have multiple values of resistor than multiple values of capacitor. So yeah, this looks like a pretty good start, except I know for a fact I don't have any I do have 10K resistors. Okay, so let me wire this up so y'all can do your own jig while I grab the resistors I need. Okay, maybe I have a couple of these already here. I have 100 ohm because I needed that from last time. And I have this, and then I have my NPN, which I pulled off. Oh, and I have a 10K. So what I need is...
This is the first time anyone's ever done this, by the way.
Oh, you're playing with your pencil.
Yeah, I've got a pencil.
That's cool.
And this is all on.
Oh, neat. How did you export it in?
Yeah, it's freaky. So
That's
you
freaky.
Can, yeah, so if you want to do this again, you can, if you want to draw on this, you can draw on this. I can hand this to you.
Okay. Oh, I see. Yeah, that's a good idea.
Yeah.
Okay, so I found a 2.7K resistor.
So what screen do you want to go
Oh, no, I'm not ready yet. I'm still digging out resistors.
to? Okay.
And I'll let you know. You can keep drawing. Hair artiste.
All right.
I'm going to have to find a... 5.6K and 20K. I'm trying to remember if I had that bundle of resistors. That's what I was unable to find last time. Okay, 22, and then I want 33K. I don't have 33. Oh, no, I do. Oh, these are all out of order. Ugh, these are all out of order.
Use the Sterling top.
Huh?
Sterling top of it.
Oh. Okay, hold on. I gotta find this last resistor. I have a 27K, I have a 51K. I'm okay with a 27K. I'll adjust this all later, maybe if necessary. Okay, 27K. $47. That's weird. Like my resistor pack just doesn't have 33. Okay, that's cool. All right, so I can. Should I draw this thing, or what should I do?
Yeah, 1 moment.
Okay.
So, are you going to be showing off this?
Yeah, maybe I'll just draw just for fun. I'll redraw the mini schematic, and I'll use colors. Okay. We're just doing crazy science.
This is what that would be.
Okay. And then it doesn't detect your hand, huh? Okay.
Yeah, so here we are here.
Whoa. Hold on. No, this is erase.
Yeah.
Okay, no ruler. Sorry, I'm learning this stuff too. So I have.
No one's done this before.
Okay, hold on. I have to go black. How do I Why is it not drawing?
I think.
Oh, I have to select pen. Okay. Do I want pencil or pen?
Whatever you want to do.
Okay. So this is my DC plus AC MEMS mic. Okay, this is kind of weird. I'm not used to
Yeah. Well,
doing this. And then I'll switch to red to indicate power, and then maybe I'll do some. Okay, I have to get used to. Can I make the lines thicker?
yeah, I think you can use that one. Yeah, that one. That one's a more thicker.
This is, but it's like 1 pixel.
Yeah. So this is just a notes app.
Oh.
I only got this working 1 minute ago.
Yeah, no, I know
So,
that.
We'll.
Okay, that's pretty cool.
Yeah.
So then gain equals negative RL RE, and this is 100 ohms, and this is 2.7K. So the gain is going to be negative 27, which is fine, right? Because I wanted something between 5 and 40. And then I'll just read this straight into my microcontroller analog digital converter. Okay. I just have to like.
Yeah, we'll get other apps.
Yeah,
At some
I just need a little bit of.
Yeah, we'll get other apps. This is the first thing I could find.
Yeah.
It
I mean, it's definitely way nicer
It's way better
than drawing on a piece of paper. I mean, I like pieces of paper, but
Yeah.
this is cool. All right, so this is your this is basically just the circuit. So basically you just want to you want to tweak this stuff. Oh wait, let me try pencil. Oh, pencil's weird. I don't want that. Okay. All right. Yeah, that's not visible. You have to use the pen. I don't know anybody else doing live electronics broadcasts with
With an iPad
with an
Pro
iPad
and
Pro and a
pencil?
pencil.
No, this is absolutely it. I'm at the end.
You're at the, okay. All right, so let's build the circuit. Enough jibba jabba.
Okay, now what are we gonna do?
So we're going to just go to the overhead. I mean, I can just do it on the overhead,
Yeah.
but then we'll go to scope cam.
Okay.
Okay, so
Here we go.
get the transistor. Oh,
You had me zoom in a million years ago.
no, there's something, it's off-timed, but that's okay. It doesn't really matter. Like it's off by a few seconds.
Oh,
Okay, so I got the transistor. Actually, I'm going to put it this way. Sorry, this way is correct. So put the emitter resistor in. Got my 100 ohm resistor. And then I have this is a 2.7, so this is my emitter-based collector. And then I have a 10K to ground. And then a 27K to VCC. And then finally, I will put a capacitor from the base to the DC output. Okay. Cool. I'm ready for scope cam. Yet again. Okay, so we're back at scope cam, and I'm still connected just to the DC output of the MEMS mic, so I can speak, and it's at still like 50 millivolts peak to peak type thing. And then at the base, I still have that 50 millivolts. This is through a capacitor. If I DC couple it, I will see my my DC offset is 800 millivolts. So you remember we wanted to have 0.1 volts plus 0.7 volts, about 800 millivolts. So good. And then we can check the emitter. Okay, it's a little bit high. It's like 1.23 millivolts. Remember I said it's like you can't you can't assume it's going to be perfect 700 millivolts across the VBE. Now, I'm using 5% resistors. I also didn't have the exact values. When I go into production, I'll pick like the perfect values because 1% resistors cost less than a tenth of a cent. So whatever, getting the right values is pretty easy. And finally, we'll look at the collector. So the collector is a little low at 280 millivolts, and so you can see that I can speak, but it's pegged. Like you're only seeing spikes go above this DC. So I want to reduce that 2.7 K resistor, and I'm going to maybe take it down to 2.2K, which I happen to have because it's my favorite value. So I'm going to remove this and replace it with the 2.2K. And then my DC offset just went up like about 100 millivolts because, again, I don't have that, you have less current going through the load resistor. I have a little bit less gain now. Now I have about 22 times gain, but still better than nothing. Still 22 time gain means that right now I'm at 200 millivolts per division instead of 20. And so you can see I'm getting at least, just speaking from far away, or speaking from about 6 inches away, I'm getting about 500 millivolts, maybe a little bit more. Let me trigger. I'm getting about 500, maybe 600 millivolts peak to peak, and then I'm detecting audio even when I'm a little bit farther away, which is kind of what I wanted. Like this is a good distance. I want it to be able to listen to audio even from about a foot away, which is kind of what I've got going on here. And then, I can tweak the gain a little bit more. Another thing I can do is on the microcontroller, I can mess with AREF. So bringing AREF down to like 1.1 volt, I'm pretty sure that the Atmega 3204 doesn't do 1.1 volt AREF internally. I think you do 2.56 volts. That's still better than nothing. And like, I kind of like this. Like I'm getting, getting 200 to 400 millivolts means I'm actually going to be able to probably, well, I can do the math actually. So if 2.56 volts is full range and you're doing 10-bit ADC divided by 2.5 divided by 1000 is about 2.5 millivolts. And so here I'm able to get, I'd say that this is like 250 millivolts peak to peak. So, I'm going to get a fairly good range. I'm going to be able to get, about 100, 0 to 100 as my range. And then there's another thing I can do, although I don't think I'm going to do it, which is you can have a differential gain into the Atmega 3204. I don't think that makes sense. I don't want to have like any more gain there. I can also start like tweaking these values a little bit. I can, get that. Remember, I had the bias on RE. I think it was a little bit high, and that's why I had to reduce the gain. Yeah, it's like 142 millivolts. So if I grabbed 150 ohm resistor, just 1 second, 68, 110, 120K. This is like half of my job is just digging through. The resistor pile I have. I think I'm missing a bundle of the resistors because I have 36 and then it goes to 110. And then it goes straight, oh, here it is. So let's say I wanted to test what actually happens when I set a bias of exactly 1 millivolt. So I'll pick a 150 ohm resistor. And of course, you can't do this in production. You can do this on a breadboard, but in production you have to kind of decide what resistors you want to use. So what I might do is actually look at what other resistors I've got and swap those out. So I'm going to swap out my emitter resistor just for now. So now I'm going to have a much higher voltage. Yep, so you see I skipped up. Before it was about here. And now I have 1 volt DC gain, which means I can actually re-bump that RL up a little bit because it's like, okay, I've got a little bit more headroom. So do that. And wait, did I totally pick the wrong resistor? Testing. Testing. I think I grabbed the wrong resistor. Hold on. This is testing. No, hold on. That's not the right one. Ah, this is it. 2.7. Sorry. I grabbed the wrong resistor. Too many resistors on the dance floor. Okay, so now we're down to a really nice mean of 500 millivolts, which is really nice. And even from a fair distance, I'm getting a good, well, I can actually measure the peak to peak with this. Maybe I'll shrink this down. I can get a pretty good peak to peak of looks like it's going up to 370 millivolts. I saw it's about 200 to 300. And if I'm a close talker, I'm going to get a good 400, 500 milliamps, millivolts peak to peak. You can see the peak to peak voltage right here. So it's kind of hard to see on the on the scope cam, but it says about 300, 600 or so. So that's good. So like basically, you can kind of, get this all going for, the cost of a transistor. So there's one more thing before we finish. Oh, can I draw on the thingy?
Yeah.
So we're not done. We're very close to done, but
Still working?
yeah. I think so, right? Yeah, erase the thing. So there's one more thing that you want to think about before you lay it out, is you want to pick, this R1 and R2. And you're like, well, what value should I use? And basically you have to make sure that you have at least 1 milliamp. You want to be able to have the base current go in without adjusting the voltage too much. But like our bias is 1 milliamp, so it's like, okay, 1 microamp. So basically just like make sure it's not like 100K or something. But you're like, okay, well, like, I'm like a strong man. I'm going to pick like, 1K, and then I'm going to pick over here, 3K. Because you're like, maybe I'll pick the same as RL. Like, okay, like I've got a super strong bias. Like, this point is never moving. This is like a rock. I'm going to draw a little rock. That's a rock. Hold on. Yeah. Okay. So you have like a super strong bias, but then you're like, wait a minute. My signal's not working. So maybe, do we have enough time? Can I show this off on the?
Whatever you want to do. What do you want to do next?
I'm going to go back to scope cam. Okay. So let's say you're like, I want to be like a rock. And so you
overhead too, or you want? I can.
No, I don't need it. I don't need overhead. And so you're. Let me grab my resistors. I had another resistor pack. Where did it go? Okay. Hold on. Entertain yourselves while I dig around for. So I'm going to remove this 10K and then this thing. $30K, 11 ohm, 510. Okay, so yeah, I'm going to put in a 1.1K instead of a 10K. So I'll do that like so. So this was a 10K, and I'm going to basically just drop it by exactly 1/10, and then I want a 3.3K resistor, 120. Well, I'll just pick a 2.2 because actually, just for this demo, actually here's it. 2.7. This is sorry, this is fine. So I'm gonna toss in this. And then, I just check what my bias voltage is. Okay, great. So you're like, okay, I have this like super strong bias, and then let's go to scope cam. We're gonna scope this out. So, now I'm like, all right, I'm ready to rock, and there's like no signal. What's going on? Why am I not getting any signal out? And then I check, okay, let's check if there's microphone signal coming out of the mic. And there is. If I blow on it, I can, I definitely get a signal. And then I'm like, okay, well, let's follow to the capacitor. So at the other end of the capacitor, I don't get, like I'm blowing on it, I'm not getting any signal. So you're like, what happened with this bias that I'm not getting signal? And you're like, well, maybe, it could be that the microphone has an output impedance, and there's like a certain amount of current it can supply. And so it's like, oh, is it that this is too much current because it's trying to drive into this 1 microfarad plus R1, R2. And the answer is that could be it, but it's actually not what it is. Not what it is. So let's go back to the iPad. Okay, so what you're seeing here is that your signal here is okay, but then your signal here is dead. Okay, so what's going on here? Well, what you have to think about is even though this is a high impedance input, your AC signal has to drive this. I'm going to use this here. This whole network here, and this network here is the same as a 1 microfarad capacitor, and then to the viewpoint of an AC signal, power and ground are DC, and so you actually have to put both of these resistors in parallel, R1 and R2. And in this case, that's 1K in parallel with about 3K, which is 2K ohms. And so you've got a, man, this is not a pretty ohm. Hold on, let me draw it nice. That's a nice ohm. So you've got a 2K here, and then you've got a 1 microfarad, and that much, those two things together create a high pass filter, right? Because you're blocking the DC, and so which is what you want. You want to block the DC, and you have a high pass filter. But the high pass filter corner frequency is 1 over 2 pi RC, where R is 2K and C is 1 microfarad, and then I can't do pi math in my head, so you use your calculator. 2 times pi times 2,000 times 1, and then you invert it, and then you multiply by 10 to the 6, and you find out that this is 80 hertz. So what you did by having too small of a resistance here is you cut off everything over 80 hertz, which is like not what you wanted. You want it, so you could really increase your capacitance, but like I don't want to because I have a happy capacitor. Like I have 1 microfarad all over the board. I don't want to change that. So that's when you want to change R2 and R1 and make them larger, and that's why you want to have this be 10K and this is 30K. Any more than that, and it's like, okay, well, the current going in here might affect it. You can do the math. I mean, I don't think it'll affect it very much. You could probably go up to, this is 50 and this is 150K. But you definitely don't want this to be in the mega ohm range because then, this little amount of current that's going in here will actually change this point. So you pick your R1, R2, not too hot, not too cold, like right in the middle there. So you have a good strong bias point that isn't affected by the base current that's leaving into the transistor, but not so strong that it overwhelms the microphone. Again, also the microphone does have about a 400 ohm output impedance or something. It doesn't want to drive. I mean, it can drive like a 2K, but like why do that? And also you do have a you want to make sure that your cutoff is fairly high. I'll probably tweak this even more. Like if this is only 800 hertz, I can boost this up a little bit. I just want to see if I could get this signal out. I mean, audio is actually not. Audio in general can go up to 20 kilohertz, but speech doesn't really. Like it stays fairly low. It's like I think maximum like 2 kilohertz or so. So that's what I would actually, I would actually do. I would actually play on my speaker various tones, and then see what the response is for that when I hold the microphone up to it. Okay, so I think I did all that math right off the top of my head. I think it's 1 divided by 2 pi RC, not 2 pi divided by RC, but it's been a while, but I'm pretty sure that's true. That's why I always use JavaScript calculators. Okay, so finally we're going to wrap up by routing this on the board. So do you want to try changing over to, yay, okay, so you can see I did the math here for 2 pi times 2k times 1, and then I divide and then multiply out by the microfarad inverted. Let's say, you know, I have a 10 microfarad and a 20k impedance. That would be 2 times 2.14 times 20k times, let's say 10 microfarad, and then invert that, and then, wait, I got my math wrong. Maybe I want it the other way. I'll look that up, and I'll update the instructions, because I think maybe I divided that wrong. Okay, so next up, I'm going to put in a MMBT 2222. No, I don't want this one. I want this one. Okay. And then 0805. Oh wait, I want to grab this one. And then I definitely have some filter caps over here. This is kind of like as I'm sketching.
Yeah, you're 46 ohms.
Okay, I'm almost done. And then maybe I'll make this a 0.1 microfarad. This is going to be about 10K. This is going to be about 33K. This is going to be about 100 ohm, and this is going to be about like 2.7, okay? And then finally, I'm going to add the microphone. Oh wait, give myself some room over here. This is for that speaker that I was working on earlier. Okay.
Are we good?
Almost. And then I actually want to think about, I want to figure out what I got wrong in my math. I think I got my high pass and low pass confused. So yeah, I'm going to basically, I mean, I'll fit this in later, all perfectly. But before I leave, I don't want to have the, I don't want to leave with bad math. So you have the AC signal, and then it's a high pass. So I'll draw my Bode plot, and so I want the high pass point to be at, oh, you know what? So it's probably actually the impedance of the microphone, a little bit more than just the fact that it's high passing too far up. Although, like, you know, you do want to have it be fairly low. So yeah, it's interesting. It's like you can think about when you have 8 ohm speakers. So like in this case, you know, my load is only 3K, but if you have 8 ohm speakers, you're going to have 2 times 3.14 times 8, or sorry, 6 headphones, 16, and then you have to do 100 microfarad in order to get, or larger to get a high pass that'll get the bass in. So you definitely want to, so for my, let's look at Aaron's, for the SPW, let me just look at the data sheet. I think it was the output impedance as well. Let's see, do I have a data sheet linked here? I don't. I should get that linked. Okay, hold on. I'm almost done. Okay, so the output impedance at 1 kilohertz is only 450 ohms. And so, yeah, like you don't want to load it too much. So I want to keep the, those resistances nice and high. And also, yeah, I want to make sure that the high pass filter has a 3 dB that's fairly low. So, you know, I can tweak it. I think I can do, one microfarad times, I think it was like 20K. And that'll give me 8. So that's actually a pretty good zone. So my first guess was correct, of having about 20K with a 1 microfarad capacitor. So that gives me 8, and then I have a little roll off before then, but that's fine. And then I'll be able to block everything below that, which is great because I don't want anything lower than 8 hertz anyways because it's not audible. But I'll still get like the low frequencies of human speech and get the high end. And then like I don't really care about a low pass filter because like I'm not going to sample that much. I'm not going to sample that fast with my microcontroller anyways. I'm going to be sampling at, like whatever Nyquist frequency, like probably 10 kilohertz about my trade-off. So I'll probably do like 20 kilohertz or so sampling. And so I'm only going to pick up those frequencies anyways. So if this was a particularly high value, right? If it was a high value, then I would put another buffer, or that's when I would actually go for an op amp for sure, because then you can go into an op amp and you don't have to worry about anything, especially with an inverting input, inverting feedback setup, then you don't have to worry about loading the output of the microphone. And electret mics in particular, like need JFET inputs from what I remember. And so like those if you're going to connect directly to electret mic, you definitely need an op amp. You can't do these games. All right, I think that's it, because I'm starting to pass out.
All right.
Whew, but I got it working.
Yeah, well, we learned a lot.
Yay.
I also learned that pushing the iPad Pro, it's just too many pixels. That like this goes.
Oh, really?
This goes 100%.
It was like 110%.
It was like crazy.
Okay.
Yeah, but we can do it. I just need to figure out. I think this is just too much for it to handle.
Okay.
It's cool.
I hope, actually, when I finish with the Circuit Playground layout, maybe I'll write up all of these little notes with links to the video, so it's like you can like watch Late Night Lady Ada. She designs this. But what's nice is that it fits in here. I fit all these parts. This is like a different thing that I'm not doing yet, and basically did it for only like 2 cents, which is kind of nice. And I don't need an op amp. And remember, if I had an op amp, I would still need I still need the AC coupling, so still need that capacitor. I need like a bias anyways because it's a single supply. So I would still need 4 resistors and capacitor. So instead of an op amp, I just got a transistor. And I'm happy with the game, so I'm happy.
Okay. All right.
That's it.
Say goodbye, everybody.
I can't do any more. Good night.